Good morning, Ms. Shuyun and my fellow classmates. Welcome to my DLOR presentation. So this presentation is an overview of two of the key fine-tuning strategies that I've used, as well as a comparison of these strategies as well as the model results. So this will not go in depth into the individual hyperparameter tuning and small tweaks and changes that I make to the model. However, for Ms. Shuyun, I already put all the descriptions in the IPYMB submission files. And for the rest of us, we have our link over here and our QR code that you can scan if you wish, and you can go to find out this Excel sheet over here. This Excel sheet has all of the changes, the results, and you can have a look at. You can even download the APK for the application if you have an Android phone. So with that, let's get right on with the presentation. This is our contents page, and we have our introduction to the CIFAR 10 dataset. This is a commonly used benchmark to actually compare different CNN architectures. So it contains 10 balanced classes with 6 types of animals and 4 types of vehicles. Some of the challenges of the CIFAR 10 dataset include small images, which has less detail. Most pre-trained models are typically trained on larger images. So when you give it smaller images, that can be a little bit of a challenge. So now we go on to our data pre-processing. For input pre-processing, we use Keras built-in pre-processed input function that is specifically tuned for each pre-trained model. For our image resizing, we resize the image to fit the pre-trained model. And for one-hot encoding, we one-hot encode the class labels. For augmentation, we apply random transformations to increase the training data variety and make for a more robust model. And it actually randomly uses any of these augmentations over here, and these are the results when we put a picture through it. For the Net5, it uses an older model architecture which has limited feature extraction capabilities. As such, it results in severe overfitting when we put it into CIFAR 10 and very, very limited validation accuracy. And we determined that the cause of the low accuracy is pretty much related to the feature extraction, as changing the FCLs don't really make a difference. So therefore, in order to fix this, we have to add more feature extraction capabilities, which we do in our next simple model, which is the custom CNN. The custom CNN uses a much newer model architecture with a larger number of filters per layer, use of global average pooling, ReLU activation function, and batch normalization, as well as dropout for regularization. And as such, you can see the architecture over here, we get a much higher validation accuracy of 91.9%. If you look at the architecture, you may find this a little bit familiar. We actually adapted this from VGG, but we instead make it more suited to a smaller input size of 32 by 32. So now we are done with the simple models, we go on to our complex models, which are also, they typically come pre-trained. What does pre-trained mean? It means it's already been trained on the huge ImageNet database, so you don't actually need to train it from scratch. Some of the complex model examples are over here, and we'll go on to transfer learning, which is the primary way that we use these pre-trained models. What is transfer learning? It actually gives us the features that we learn from the large ImageNet database. We take that and we transfer it. We bring it over, we bring all this knowledge over to our specific classification task, which is classifying CIFAR 10. There are two primary ways that we do transfer learning. The first one is fixed feature extraction. By the word fixed over here, you probably can tell that that means that our pre-trained weights are fixed or frozen. So when during our model training, we never touch or update those pre-trained weights. However, we put on our own classification layers or FCLs, and we can train it to our classification task. In contrast, for fine-tuning, we actually do, we still take the pre-trained weights from the pre-trained model, but we do update them in a controlled way and in a very controlled manner during training. Some of them, there are advantages and disadvantages to both. For fixed feature extraction, it's typically easier to develop and it has less trainable parameters. However, it does have limited model performance because the specific ImageNet database may not be perfectly suited to CIFAR 10, which is our specific task. For fine-tuning, we can adapt it to our specific task that is classifying CIFAR 10, giving higher performance, but also with more trainable parameters and more chance of overfitting if not tuned carefully. So these are the results, and I'll first like to preface these results by saying that we need to set a baseline for our results. And so our baseline over here is the results attained by our custom CNN, which is 91.9%, and also the human accuracy, which is about 94% when it comes to classifying CIFAR-10. In this case, you see VGG performs the worst of all the models, and it's also the oldest, and also the efficient net, which V2B0, which is our newest model, performs the best. However, if we look at it in contrast to our baseline, you'll see that the validation accuracy is actually quite a lot lower than our baseline in this case, and as such, it's not really performing ideally. And this is because we are unable to actually adapt the feature extraction to our specific problem. So as such, we want to do something about that. Do you think we can do better than that? Yes. And now we go on to the next one, which is our fine-tuning strategies. So there are two primary fine-tuning strategies. These are not specific steps, but rather they are overall strategies that we use to fine-tune. One of them is partial fine-tuning, where we set the last few layers, which typically handles more specific high-level features, we set it to trainable so that it can adapt to the specific task. In contrast, for complete fine-tuning at a lower learning rate, we go with a different method of fine-tuning, where we first run the model, so we do a dot fit with everything frozen, all the weights frozen, and then after we dot fit again, but this time we set everything to trainable, but we significantly lower the learning rate. For partial fine-tuning, we typically use it when the dataset is similar to ImageNet, and it's typically less computationally expensive because it has less trainable parameters. You're only training this part. However, for complete fine-tuning, you typically get better results because you're training all of the, you're actually training you're training the entire model again. However, because we have more trainable parameters, it can be computationally more expensive. So now, let's look at a comparison of the results of both fine-tuning strategies. So for the results, here are our baseline again, our custom CNN and human accuracy. And you notice that all of our pre-trained models actually do better than our baseline now. So that's a huge contrast to before. And you'll notice that the complete fine-tuning does consistently better in the same model, consistently better in validation accuracy and validation loss. So you see a decrease in loss, increase in accuracy, and as such, we determine that the complete fine-tuning method is typically better for most pre-trained models, at least when it comes to the CIFAR-10 classification task. So for the rest of this project, we'll use the results from here. And right now, let's go on to compare performance metrics. This is very important because different families of models are optimized and prioritize different things. Some models, like MobileNet, just prioritize efficiency a little bit more. So we don't need the absolute best performance, but we want efficiency. We want it to run on smaller devices. Whereas EfficientNet, despite the name, EfficientNet V2 at least, despite the name, its prioritization is on high performance. And as such, it will be a little bit more complicated than MobileNet. Yeah. So therefore, we have these metrics, yes? Yeah, okay. Yeah. So we'll compare using these metrics: classification accuracy, file size, training time on our tensor processing, and also a pet dot this classification rate, because this is the pair of most confused classes. So by using this, we actually find the lowest common denominator, and we're able to find how the model actually performs. So this is our model comparison and results overall, and you'll notice that these two models have the lowest runtime of or at least training time of all of the pre-trained models, and it still scores fine. And for our EfficientNet V2M, this has the highest performance and the longest training time. So therefore, our best models, just to sum it up, MobileNet V3 is the best for mobile, ResNet 50 V2 is better when you need slightly higher accuracy, and EfficientNet V2 VM gives us the best possible accuracy, but with much longer training time as well as more powerful inference needs. For our dynamic learning rate schedulers, I'll just run through this real quickly. We tried two dynamic learning rate schedulers. One of them is the reduced LR plateau that I think all of us are pretty familiar with. It just steps down the learning rate quite quick, in steps. And then for one with cosine decay, it takes a more proactive approach. So you need to plan it out in advance, And if you plan it in advance, you'll see how the curve gradually and smoothly reduces the learning rate. This can be beneficial for larger models, and as well as when you want more control over how the learning rate declines. Because for this, the only parameter you can pretty much set is factor and patience, and you can't fully control exactly how it works. But this one is a very detailed control over the learning rate.
In the interest of time, later you want to just stick into your demonstration.
Yeah, this is my deployment slide. Yeah, so this is my deployment. So I'll be demonstrating the Android deployment. So I put it over onto my phone. And okay. Alright. You can see this is my handphone over here. I'll push this here and let's grab some pictures. Alright. So over here we have a picture of a bird. As you can see, our model correctly classifies this. We have a car over here. And interestingly, even though the car door is open, we have a lady over there blocking some parts of the car, but the model is still able to classify a large part of it. And also the background is a little bit different from what I think most of the models train on. And here we have a car without wheels. How's that sound? Alright, here we have a cat, which is correctly recognized as well. It's an animated cat. This is a real cat. We have I think this is a retriever, I think. Yeah, the dog is correctly recognized. Here we have a sausage dog. Really, really cute. I love sausage dogs. And then here we have a frog, an airplane, and yeah, that's about it. Alright, so I'll move on to my, I'll just quickly run through. For our deployment, I did integer quantization, which reduces the model size and supports hardware accelerators like Google's Edge TPU. And with proper calibration, these quantized models can perform pretty much almost the same, very, very negligible amount of model accuracy loss. As you can see, my phone was running an integer quantized model. Now I'll go on straight to the conclusion. What are some areas that I feel could have been refined or improved? And I'll just shout out to those guys outside the door who are watching. Okay, so firstly, learning rate scheduling. So earlier I mentioned in my slide that I did 2 learning rate schedulers. However, there's another one that I've seen quite often in CNN research papers, which is decay with restarts. Ensemble learning would be great for our cat-dog classification problem. Using TPU will be great for increasing training speed. I've done that for my EfficientNet. And also the vision transformers and convolutional vision transformers. These are models that score really well on CIFAR 10 and ImageNet classification, and I would like to try them for future projects. And with that, thank you so much for your time. And do you have any questions? We should. That's the references.
3 minutes, I want to take up 3 marks. So, what was your major? Because I know you started very early for your project. So, what is the major pain points?
I think one of the biggest pain point for me was that because I started early, I kind of had to try a lot of stuff myself, and I didn't exactly. Okay, firstly I started with Kaggle, right? Because that was really where we got where we look at the CIFAR 10 data set and stuff. But I got a lot of wrong information from Kaggle. So there were a lot of people who actually posted the Kaggle notebooks. They got a lot of the hotness or the votes is very high, but it ended up being not exactly correct. So sometimes I write the code already, then I realized that a few weeks later that actually the code is not right, that's not the right way to do it. So I end up having to iterate on it. But through that iteration and through all that process, I think I really learned a lot about this CNS. Of course, it is still very basic, and I would really like to improve a lot in the future. Maybe try out some, as mentioned here, some of the refinements that I would like to try. And I think I've learned a lot from this process of iteration, tweaking, fine-tuning. Yeah.
Thank you.
Yeah, thank you.